Okay. Good. Thank you very much. I'll pass over to Gabor, who will be guiding us through today's procedures.
Thank you, Klaus. We're a little bit behind schedule, so I will keep it short. It's a great pleasure to introduce you Christoph Mathys. Of course, many of you already know him. Some of you probably have been using his model, the HGF, that he's going to probably present to you today. So the background of Christoph is quite interesting because first he did a master's in interdisciplinary sciences here at the ETH. So welcome home, Christoph. I'm sure it feels good to present at home. And afterwards, he did another master's in psychology and psychopathology. And then he did his PhD in information technology under the supervision of Klaus. So I think he's got this perfect interdisciplinary background to this kind of research, which is, well, we call it here computational psychiatry. So welcome, Christoph.
Thanks, Gabor, for the introduction. And thanks, Klaus and Rike, for letting me be here. I apologize for being a sweaty mess. I will remember never to run before giving a talk in the future. We will talk about hierarchical probabilistic inference. And even though I have a long time slot, this topic is a bit broad for 1.5 hours. So what I propose to do is that we start looking at general kinds of inference problems as we face them in science in general. And we shall first look at what kind of questions we're confronted with and how we can deal with them. And then I will give you an example of a general Bayesian inference with a very simple toy data set comprising only 13 data points. And from then on, we will deal with hierarchical models. We will progress to these hierarchical models, and within the field of hierarchical models, we will look at hierarchical models of time series, and especially, as already promised, the HGF. So let's jump right in and ask this question. Does chocolate make you clever? This was a few years ago, very prominently on the BBC News and in all kinds of other news outlets. Eating more chocolate improves the nation's chances of producing Nobel Prize winners, or at least that's what a recent study appears to suggest. So let's look at that study. This is the graph from the study. Chocolate consumption, kilogram per year per capita, and Nobel laureates per 10 million population. Many of you will be gratified to see Switzerland here. So there's an impressive correlation here. Correlation is about 80%, and the p-value is very, very small. And what's more, this actually appeared in the New England Journal of Medicine, which is one of the most prestigious medical journals. So this must be true, right? This is an established scientific fact. Look at the p-value here. Huh? Such a p-value cannot lie. So if we wanted to go about finding out whether this is actually true, what would we have to do? What would be a sensible procedure? What's the kind of questions we have to ask? So we see that this is a question referring to uncertain quantities. And like all most scientific questions, it cannot be answered by deductive logic. Nonetheless, we can make quantitative statements. And we can rephrase the question here, will I win the Nobel Prize if I eat lots of chocolate, probabilistically by saying what is the probability of winning a Nobel given that I eat lots of chocolate. So I know you've seen lots of these conditional probabilities. This is a conditional probability. This slash is vertical slash is read as given. Nobel Prize given lots of chocolate. So to answer this, we have to learn to calculate such quantities, and the tool for that is Bayesian inference. That's all it is. Bayesian simply means logical, and logical means probabilistic. The great physicist Maxwell said this in the mid-19th century: the actual science of logic is conversant to present only with things either certain, impossible, or entirely doubtful, none of which, fortunately, we have to reason on. Therefore, the true logic for this world is the calculus of probabilities, which takes account of the magnitude of the probability which is or ought to be in a reasonable man's mind. So, in what sense is probabilistic reasoning logical? And we know the answer to that because of R.T. Cox, who in 1946 showed that the rules of probability theory, there are just 3 rules, you've already seen them in other talks, but we'll see them again, can be derived from 3 basic desiderata. The first is the representation of degrees of plausibility by real numbers. So if you admit that you can put a number to the plausibility of a statement, then, and if you also admit the other desiderata, you will have to reason using the rules of probability. You can, of course, deny this. You can say this is a kind of quantification that I'm philosophically opposed to. You can say, I don't think I can put a number on the plausibility of the statement. But if you do admit that, then the rules of probability follow. If you also admit that there should be a qualitative correspondence with common sense. Now, this is well defined mathematically by Cox in his paper, but it basically just means that if you get evidence for statement A being true, then the plausibility number of statement A goes up. If you receive evidence that might indicate that A is not true, then the number goes down. And number 3 is consistency. If you admit that there should be consistency, so that if there are 2 ways to calculate the plausibility of statement A, that they should give the same number. If you admit those 3 things, there is no way around the rules of probability. And here they are. The first is normalization. All probabilities for one kind of event A sum up to 1. If we have 2 kinds of events, A and B, and we look at their joint probability, and we sum up over all the possible outcomes of A, then we get the so-called marginal probability of B. That's called marginalization, and is also called the sum rule of probability theory. And then we have conditioning. This is the product rule of probability theory, and it's extremely important for Bayesian inference. This means that the joint probability for A and B is the conditional probability of A given B times the marginal probability of B, or the other way around, the conditional probability of B given A times the marginal probability of A. And by applying these rules, one can reduce common sense to calculation. Probability theory is nothing but common sense reduced to calculation. That's what Pierre-Simon Laplace, the first guy who really saw the meaning of all of this, said in 1819. Now, by simply using the product rule of probability, we get Bayes' theorem. So, as we saw on the previous slide, the conditional probability of B given A times the marginal probability of A equals this here, which is just the other way around. Now we simply divide by the marginal probability of A. And the marginal probability of A can be decomposed like this as the marginalization over B of the reverse here. And this expression is then called the model evidence. This is Bayes' theorem. You've seen it many times before now. Turning to the chocolate example again, it's immediately clear that our true question of interest, the probability of the Nobel given that I eat lots of chocolate, is not directly accessible. But we can go the other way around. We can assess the probability of eating chocolate if we have a Nobel Prize, just by going out and asking Nobel Prize winners, how much chocolate do you eat? That's a number you can collect. It may be a bit arduous, but yeah, you can do that. Then you know the base rate of winning Nobel Prizes. You know what proportion of the population has a Nobel Prize. And you know the base rate of chocolate consumption. Those two are not hard to find. And if we have all of those three, we can calculate this. So inference on quantities of interest in neuroscientific studies has exactly the same general structure. And now for what we call these beasts, this is the likelihood here. These are our observations, and these are the parameters for our observations. This is the prior. This is the so-called evidence, or model evidence. This is the posterior. And the likelihood and the prior together are what we refer to as a model, or more specifically as a generative model. And in computational psychiatry, we have this situation here. We have a model of what's going on in the brain or in the mind. And we have a likelihood function that says, given what's going on inside, which is parameterized by theta and by our model M, we have a model of what kinds of observations Y we are likely to make. These observations can be behavioral, they can be physiological, or any kind of observation. But the actual problem we want to solve, what we want to publish the paper on, is that based on our measurements, we believe such and such was happening inside. So we have to solve the inverse problem. We have to find the probability of certain parameter values given our observations and our model. And that's why the whole framework of Bayesian inference is fundamental to computational psychiatry. So that's the way inference works. We have a likelihood, we have a prior. This together gives us a generative model. And here, you've already seen this graph, I believe, is an example of Bayesian inference with the prior in green, the likelihood in blue, and the posterior in red. And all you need is Bayes' theorem here. So let's turn to our little toy example. There are two manufacturers, A and B. They deliver the same kind of component, and they turn out to have the following lifetimes in hours. A here, B here. Now, let's assume prices are roughly comparable. We'll go into that in more detail afterwards. From which manufacturer would you buy? Anybody who's buying from A, please raise their hand. We have a few. Yeah, we have about, at least 10 people. Anybody who's buying from B, raise their hand. Slightly more. So anybody, whether you're buying from A or from B, why are you buying from A or from B?
Products of B seems to be better. They have longer lifetimes.
They have longer lifetimes, but you have 4 numbers here and you have 9 numbers here. So how did you do that generalization? You're making a general statement on the basis of a few data points. So,
because he had the prior belief, as I had, that these are comes from Switzerland, and therefore that number would just
that's how your priors
continue very robustly.
Can influence your inference. Right. They're more consistent in B, okay. So to put it a bit more mathematically, there's less variance in these than in these. So that's one reason. But if those had been all had been around 10, 10.1, 10.2, 9.9, That would be very consistent, wouldn't it? Would you also have bought from B then? Higher and more consistent. So there's at least two criteria at work here. So the question is, how do we compare such samples? And usually the answer I get, those are very sophisticated answers, I have to say. Usually the answer I get is by comparing their means. So that's what people usually first do, and it's actually a sensible thing to do. So why do we take means? There are deep theoretical reasons why we like means. We may not know it, but it's a good idea to take the mean, because if we take the mean as our estimate, the error in our estimates is the mean of the errors in the individual measurements. And this will cancel in the long run. Taking the mean as the maximum likelihood implies a Gaussian error distribution. So this is how Gauss found his distribution. So he measured the positions of stars because he was a great astronomer. And at some point he began asking himself, well, what kind of error distribution am I assuming in doing that? And that's how he found his distribution. And a Gaussian error distribution is appropriate because it reflects the prior knowledge about the errors whenever we know nothing about the errors except perhaps their variance. And you see the relevance of the variance here again. So, what next? Let's say your boss told you that you need to make that decision and you had to come up with a reason. So if you just go to the boss and say, I'm buying from B, he says, that's not good enough. I want a reason. I want numbers. What are you going to do? You're all trained in quantifying stuff. What are you going to do? What are you going to... Or you could just tell him the means. Can I go back? So, one thing people mostly do is a t-test. The good thing about a t-test is it takes account of both things that Brian mentioned. It takes account both of the variance and of the mean. And it tells you whether there is what classical statisticians call significant difference between the two samples. So what we learned when we did our undergraduate statistics training is that we first have to see whether the variances are different before we can decide whether to do an equal variance or a unequal variance t-test. So we see that the variances are not significantly different. The p-value is 0.33. So we do the equal variances t-test, and we see the p-value is 0.66. So the means are not significantly different. It was terribly unscientific of you to go for one option or the other. There was no significant difference. So you go to your boss and you say, well, we can't decide. I've done the t-test and then the boss tells you to go home because he can look at these numbers and he knows B is better. And if the statistical procedures you use cannot reproduce this that he can plainly see just by looking at the numbers, he has serious doubts about your statistical procedures. It's not satisfactory. So we turn to a superior instrument, and that is probability theory, just Bayesian inference. We can actually calculate the probability that parts from B live longer than parts from A. And all we need is the rules of probability theory. So, our procedure in brief will be to determine our question of interest. What is the probability that? Then we specify our models. And that means likelihood and prior. And in saying models, I meant to use a plural because we're going to compare models in the end. We calculate or approximate the full posterior using Bayes' theorem, and then we compare our models. So we check their predictions, we look at the model evidence, and so on. And then we take the model we like best, or in some cases we might also want to average over our models, and ask the question of interest of the posterior. And all we need is the rules of probability theory. And sometimes we might encounter a nasty integral, but that's a technical difficulty, not a conceptual one. The conceptual questions here are easy to solve. So, I've set up a Bayesian inference example, this Bayesian inference example with the two manufacturers on GitHub, and we will just turn to you can download it there. You will get the slides, and you will have the URL here. So I will just switch to my Jupyter notebook that you can find on GitHub. Here it is. Let me increase it a bit in size. I hope that's possible. It's hard to read for you, right? So the text doesn't really matter. I wouldn't have read it out anyway. You can go to the website and read it yourselves. What we do is we use R in this context here because the tools that are available in R are, at the moment, simply the best. We input all our data points, the 13 ones for manufacturer A and the 4 ones for manufacturer B. We build a data matrix X, and we output the numbers again. Maybe if I go to the GitHub page. Yeah. You can see it a bit more nicely here. When we graphically look at these data, we have the lifetime in hours here. These are so-called violin plots. The data here, manufacturer A, manufacturer B. Now, in the classical approach, we do the t-test. You can see it's exactly the same result as we saw before in the slide. And now, we also want to build an actual model. We want to use a model. So we do a linear model, LM, in R. We say the lifetimes T are determined by which manufacturer I'm buying from. And you can see this is exactly equivalent to doing the t-test. We have the p-value of 0.0665 here, just the same as when we did the t-test here. It's 0.665. So it's exactly the same. And this is important to see that behind the t-test, you always have a linear model. It's basically a very simple kind of linear model that you're testing in a t-test. And now you can write down your model. Y, or in our case, the lifetimes, depend on an intercept, on a coefficient for the manufacturer, an indicator for the manufacturer. This is XMF for the manufacturer, plus error. So something very similar to the kinds of models that Klaus just wrote down. And another thing that occurs to us is that lifetimes have a lower bound at 0, a natural lower bound at 0. There cannot be a lifetime less than 0. And in such cases, it's mostly appropriate to log transform your measurements and assume that the errors in the log reaction time model will be Gaussian distributed. And if we do that, that's how our data look. Actually quite similar. It's just that manufacturer B is now even more narrow with respect to manufacturer A. This is the variance that Brian mentioned. So when we do that, when we now use log t in the linear model, it doesn't really change our inference. So the p-value is still about the same. Another way to do that, and this is just to illustrate the syntax in R, is to use a so-called GLM function, where you just, which is a generalized linear model, where you use the Gaussian family with a log link. And as appropriate, this basically, and this is fit in a different way. This is fit by a numerical algorithm and not by ordinary least squares. And it gives you very similar input. Results as appropriate, as it should. But now let's turn to the Bayesian approach. This has all been the classical way to do it. Now, in the Bayesian approach, we're still going to use this model. We're going to say our outcomes y are a linear function of our data on the manufacturer, and we have an error that is Gaussian distributed with a certain variance, sigma. So we have three parameters in our model: the intercept, the manufacturer coefficient, and the variance. And on all of these, we may now place priors. And this is a huge advantage when doing Bayesian inference, because implicit in all classical inference are so-called flat priors. And we'll talk in more detail about the pathology of that flat priors can lead to. But very simply, it's it is important to regularize your inference. And so what we get when we specify priors here, we can use the nice package rstan arm, and we get a posterior distribution on all of our parameters. We can use these kinds of plots here, or we can use fancy violin plots. And when comparing different models of this, we can apply more shrinkage. So we have a second model here, fit2 in yellow, and we can see how the effect of manufacture is shrunk towards 0 because we applied more shrinkage. And if we do the log transformation again, we have inference like this here. Again, we have most of the probability mass of the manufacturer from B greater than 0. So now, when we check our models, we see that there's a problem with the first two fits. This is the one with less shrinkage, this is the one with more shrinkage, but when you look at their posterior predictive distributions, they all have predictions going down into the negative, and this doesn't make any sense. So the predictions of your model have to make sense. So we can now question how much longer parts from B live, and we have a posterior distribution on that. And in the violin plots, I've plotted the 80% quantile here. So basically, no, it's the 20% quantile. So from this line onwards, upwards, we have an 80% probability. And the blue line is the 3-hour limit. And if we assume that it is worth our while to buy from manufacturer B as soon as we as they live at least 3 hours longer than from A, then, at least in our model that makes most sense, that is actually the case because the 80%, the 20% line is above the 3-hour limit. Then you can also look at some formal model comparison measures there. But now let's return to the slides. This was the procedure. And we have here another 2 slides on the formalities of model comparison. I think you've seen this in other talks a few times. So you can just look at the slides once you get them. We will also not speak about informative or uninformative priors. I will just very briefly, this is the last slide before I turn to the HGF, talk about hierarchical models. A non-hierarchical model consists of a likelihood and prior. The likelihood gives the probability of the observation given parameter values, and the prior gives the probability of parameter values. And what we have here is the non-hierarchical model with simply likelihood and prior. But now, as we saw, we had hyperparameters that parameterized our prior. And these hyperparameters can now have a hyperprior. And that's where we add another level to the model, and so on. And models with multiple layers like this are called hierarchical models. They're useful in various contexts, and we will here deal with the hierarchical Bayesian modeling of time series as promised. Okay. Time series. A shamelessly artificial example. Some of you may already know this. Imagine you're on a boat, and you've lost your modern equipment, you're in a storm, you're trying to get back to shore, and you've just seen a lighthouse appearing on the horizon, but you can only see it when you're at the top of the wave, and not when you're down in the trough. Your only chance to determine your position is to measure the angle between north and the lighthouse. At some point, you start measuring, and these are your measurements: 76, 73, 75, 72, 77. What number are you going to base your calculation on? Ah, the mean, yeah. I'm never asking trick questions, so yeah, it is the mean. 74.6. How do you calculate the mean? And again, this is not a trick question. How do you calculate the mean? Serious question. By summing them all together and dividing by their number. Yes, exactly. The usual way to do it is this. We sum up our observations x, and we divide by the number of x's. But if we have lots and lots and lots and lots of information that we have to average, that becomes a memory problem. So you would have to remember all of the xi, and that would become a burden. So it turns out we can also update our mean sequentially. So after some algebra on the next slide, we can see that if x bar n is our first mean, our previous mean, and xn plus 1 is our new observation, then I can update x bar n to x bar n plus 1 by taking x bar n and adding to it the difference between the new observation and the old mean, weighted by 1 over n plus 1. This is the proof. You can take a picture or download the slides and verify this at home. Graphically, it's like this. You see the first observation at 76. This is your first mean. Then your next observation at 73. Now the mean goes to the middle. Applying our equation here, then the next observation is 75. The mean moves slightly towards it. 72 now. The mean moves towards 72, and so on until we're at x bar 5, which is again 74.6, as it needs to be, as we know from the procedure we used before. So what are the building blocks of this? We have a prediction. We have our previous mean x bar n. We have the new input, x n plus 1. We have the prediction error. This is a prediction error. Because we have a prediction, we have a new observation. Observation minus prediction is prediction error. Very, very simple. And then we have a weight on the prediction error. 1 over n plus 1, and we can interpret this as a learning rate. Because the higher this is, the more we will move towards our new observation, and the lower it is, the more we will stay with our prediction. Now, is this a general pattern? I mean, this is just a very simple, primitive example, and it's only about mean updating, but is it a general pattern? Does it in any way apply to Bayesian inference? And of course, the answer is yes. Bayesian inference simply means inference on uncertain quantities according to the rules of probability theory. Again, so agents who use Bayesian inference will make better predictions, provided that they have a good model of the environment, which will give them an evolutionary advantage. And we may therefore assume that evolved biological agents use Bayesian inference, or at least a close approximation to it. This is why Bayesian inference is so important to us in studying biological agents in humans and computational psychiatry. So is Bayesian inference based on predictions that are updated using uncertainty-weighted prediction errors? Yes. Updates in a simple Gaussian model. Now, the same example again. The boat, the lighthouse, everything. And before we make the next observation, our belief about the true angle of theta can now be described by a prior. So we say we have a prior belief on the true angle theta. This is characterized by a mean mu theta and by a precision pi theta. And the precision is simply the inverse of the variance. And the likelihood of our observation is also Gaussian with a precision pi epsilon, because our observations aren't entirely precise. The boat's moving while we're making our measurements, and our instruments are not entirely precise. So we have a certain variance, and this is the inverse of this variance in our measurements. So this is our likelihood. Given the true angle theta, our observation x will be distributed as a Gaussian around the true angle with a certain precision pi epsilon. Now, Bayes' rule tells us that the posterior will be Gaussian again. And this is the new mean, the posterior mean, mu theta given x, of our belief after making observation x, and this is the new precision. And the question now only is, how do we get the new mean and the new precision? And it turns out that these updated equations have an interesting structure. So the new precision is simply the prior precision plus the observation precision. Very simple update rule. And the update rule for the mean is that the posterior mean is the old mean times a weighted prediction error. Because this is our new observation, this is our old mean, and we have a weight on the prediction error here. So this is the same structure again. Prediction, prediction error, and our weight, the learning rate, is a precision ratio. How much we're learning here to how much we already know. And this pattern is not specific to the univariate Gaussian case, but generalizes to Bayesian updates for all exponential families of likelihood distributions with conjugate priors. The analogy with simple mean updating goes further. We can rearrange this algebraically, and then we see we have the same 1 over n plus 1, or now nu plus 1 structure again, where nu is now not a natural number, but simply a positive number. So in true biological agents, there is still something missing in what we described. if you have the situation of a human agent or another biological agent navigating, negotiating its environment, something was missing here. What was that? There's an additional problem that needs to be solved. The boat is moving, exactly, yes. The world is dynamic, the world changes, and all the inference we've described up to now was on static quantities. And you saw that in the mean updating, the learning rate went down and down and down and down with 1 over n plus 1. The more n's we have, the lower the learning rate is. And this makes sense if stuff doesn't move. But as soon as stuff moves, we have to keep the learning rate at a certain level, at an appropriate level, to keep learning about this. And to disregard old observations, we have to have a kind of forgetting mechanism. So we have this dynamic cycle where we have an agent and we have the world, and there are two interfaces with sensory input and action, and there are true hidden states of the world, and the agent has to infer the true hidden states of the world through its sensory input and in turn determine action on the basis of its beliefs about the true hidden states, and these actions by the agent again influence the agent, the world. And the dynamics are missing. So how can we take into account that old information becomes obsolete? If we don't, our learning rate becomes smaller and smaller because our equations were derived under the assumption that we're accumulating information about a stable quantity. What's the simplest way to keep the learning rate from going too low? We can keep it constant. So what we do is we take our mean updating equation. This is still the same equation. I've just shifted around the n plus 1 and n. We have n plus 1 here and n here. Now we have n and n minus 1, so n plus 1 becomes n. So we take our 1 over n, and we simply replace it by a constant alpha. And this is called Rescorla-Wagner learning. And it's been very successful at describing how biological agents learn. It's been around since 1972, and people still use it today. But does a constant learning rate solve our problems? Well, partly. It implies a certain rate of forgetting because it amounts to taking only the 1 over alpha last data points into account. But if the learning rate is supposed to reflect uncertainty in Bayesian inference, then we need to take account of two things. The first is we need to let alpha reflect the right level of uncertainty at any one time, and we need to account for changes in uncertainty. What we really need is an adaptive learning rate that accurately reflects uncertainty, and there are various attempts to do that, and all of them try to deal with these three kinds of uncertainty. Outcome uncertainty. This is the irreducible uncertainty that you have when you, for instance, flip a coin. Even if you know the parameter, that is 0.5 in a fair coin, you will still have uncertainty about the outcome. You know the parameters of your model exactly. This is the uncertainty that remains, the outcome uncertainty. Now, if you don't know the parameters of your model, you have informational uncertainty. If somebody just gives you a coin and you don't know whether it's fair, you first have to find out whether the parameter at work in this coin is actually 0.5. And you can do that by flipping the coin 1,000 times, and then you'll have a pretty precise idea about what the probability of heads and tails is in this coin. It won't resolve your outcome uncertainty, but it'll resolve your informational uncertainty. And then there's environmental uncertainty when the environment changes. So somebody exchanges the coin, flips the coin without you noticing, and suddenly your parameter has changed, and you have to learn it anew. So that's a third source of uncertainty. These are different attempts to deal with this. And in the rest of the talk, we'll focus on this one. Just a remark about the Kalman filter. This is the most famous one of these. The Kalman filter is optimal for linear dynamical systems, but the world, the actual world that surrounds us, doesn't work in a linear way. And therefore, we need models that can deal with systems that come from nonlinear systems. So we use a generic, non-linear hierarchical Bayesian model that allows us to derive update equations that are optimal in the sense that they minimize surprise. The basic idea is this. We have a quantity of interest x1 here. And this moves as a Gaussian random walk, so that x1 at time k is Gaussian distributed at around x1 at the previous time point k minus 1. And the variance of that walk is a function of the next higher level in the hierarchy. So we have a hierarchical model here now. And at the next higher level, the same thing happens again. So x2, which determines the width of the random walk in x1, itself performs a random walk whose variance is a function of x3, and so on, up until the nth level, where we assume that the width of the random walk is constant. So at the outcome level of the hierarchy, we have our observation U, a quantity of interest x1, and an observation precision pi hat u. And this gives us the following update for our belief on x1 based on a new observation u. These are just the update equations for the precision. They look very similar as in the simple Gaussian model. And again, we have a precision weighted prediction error on the belief about the quantity of interest at the first level. And now, the crucial thing is here. We now have a learning rate that responds to uncertainty, that takes into account uncertainty. We have here the posterior precision on x1, of our belief on x1, and the higher this precision is, the more reluctant we will be to shift our belief. And the same applies to the precision of our observation. The more precise our observation is, the more we will shift our belief. So there's this counteracting force here. It's the precision of the prediction working against the precision of the posterior belief. It's a ratio of precisions, and that's important. So unpacking this learning rate, what we see is we have outcome uncertainty. This is simply the observation precision pi hat u. We have informational uncertainty. This is the variance on the belief on x1. That's sigma 1. And we have environmental uncertainty. You can see mu2. This is the mean of the belief on the next highest level. So the higher x2 is, the faster x1 moves, the higher the environmental uncertainty is. And all of this determines our learning rate. So we now have a learning rate that takes into account changes in environmental uncertainty, that takes into account our learning about the parameter we're interested in, and that takes into account outcome uncertainty. An example where we applied this to a financial time series. This is the exchange rate between the Swiss franc and the US dollar through most of 2010 and 2011. There were two salient events there. This is in April 2010, when the markets found out that Greece is broke and there was a flight into the dollar. So you see the dollar spiking up here, and the volatility, this is this level, increasing by a lot. And then in September 2011, the euro and indirectly the dollar were falling and falling and falling against the Swiss franc until the Swiss National Bank put a floor under how far the euro could fall, and implicitly also the dollar. And that's the corner that you basically see here in the curve. It's basically the dollar falling, 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 and then abruptly going up again, and you again see a spike in the volatility. And even in the volatility of the volatility, which we're also modeling here, you can see these dents. But it is most striking to look at the precision weights. This is what determines our learning rate about our time series. And especially at the second level, at these points in April 2010 and in September 2011, you see these massive spikes that just increase the learning rate to an appropriate level for a very uncertain environment. If the environment's uncertain, you have to learn faster. So there are two kinds of prediction errors that determine the updates in HGF models. Value prediction errors and volatility prediction errors. So preliminarily, this will almost certainly change. Preliminarily, I've called them vapes and vopes. Not everybody likes this, and I'm open to suggestions for better names.
Why are you looking at me?
I've heard rumors. So, but this is just a preliminary nomenclature. As soon as we've found a better one, we'll announce it. But for the purposes of today, I will still call them vapes and vopes. So value prediction errors are very simple to understand. It's simply I predict the value of my quantity of interest x1, and that's my prediction is mu1, and my observation is u. So it's simply the prediction error between where this quantity is and where I observe it. Now, the VOPs are volatility prediction errors, and these are prediction errors about how fast this time series is moving. And they are slightly more interesting beasts, but it's basically a ratio between the observed variance and the expected variance minus 1. And now you see that if the observed variance is higher than the expected variance, this prediction error will be positive and it'll move the volatility estimate upwards. And if the observed variance is less than the expected variance, the prediction error will be negative and it'll move the volatility estimate down. And we didn't construct this by hand, by the way, sorry. This came out of the variational inversion of this model. So this is a derived equation, and we just saw after deriving it how nicely interpretable it was. So this is a vape, this is a VOP, and now we can just go about constructing all kinds of HGF models based on vape and VOP updates. The procedure is described in the first HGF paper from 2011, and more details are given in the second HGF paper from 2014. The same principle applies across all of these models. What you do is you write down the generative model here. You apply a mean field partition of your variables. You derive the variational energies, and you calculate the update equations from them. And once you get a hang of it, it becomes really easy. There have been many papers based on this model. This is our workhorse. This is the binary HGF with 3 levels. Currently, more and more papers are coming out based on this model. We have a vape update down here and a VOP update up there. Just a remark on notation. Hexagons are quantities that depend on their own previous state and have a time index, of course. Diamonds don't depend on their own previous state, but they still have a time index, and circles are constants, like zeta here, for example. I'll skip this one. 3-level HGF for continuous observations. You saw this at work with the financial time series, vape, VOP, VOP. Then variable drift. We can have Z1 basically pushing around X1. So we have a drift in x1, and this drift itself changes in time and has its own volatility. Update equations can easily be derived for this. Vapes driving these connections, Vopes driving those connections. You can use this model, you can use the next model I'm going to show for this task, where people simply have to guess the next number, which is drawn from a Gaussian, but the mean of the Gaussian and the variance of the Gaussian can jump at any moment. So you have to track the mean and the variance separately, and they both enter your prediction about the next point. And both the mean has its volatility and the variance has its volatility because they can jump independently. You can simply combine this model. Vapes driving this, Vopes driving that. This is inference on one subject using that model. So the recipe in general is formulate the problem hierarchically, so imitate evolution. When evolution built the brain that supports a mind which is a model of its environment, it came up with a largely hierarchical solution. So that's what you were also doing as a modeler when you're using hierarchical inference. Separate the levels using a mean field approximation, derive the update equations, and there you are. You can invert your model. Some empirical examples. So this is a study by Sandra, published in Neuron 2013. It was a simple association learning study where the cue was either a low or a high tone, and the outcome was either a face or a house. And the association between cues and outcomes changed during the task, and subjects had to learn this. And crucially, the subjects had to predict the outcome after hearing the cue. And this is what we inferred their beliefs from. This is the model comparison. HGF1 is the three-level HGF with binary outcomes. These are truncated or in other ways adulterated HGF models that lose out. This is replicated across 3 studies. And these are reinforcement learning models by Sutton and the old Risk-Korla-Wagner model. And they all very clearly are inferior in this model comparison. And now the question, of course, is, does the brain actually care about the quantities in the HGF? Does the brain care about these precision-weighted prediction errors? And this here is a strong indication that it does. This is the precision-weighted prediction error at the second level, replicated across 2 fMRI studies. These regions here very strongly activated. And even in the brainstem, we get activation replicated across 2 fMRI studies. For the precision-weighted prediction error at the second level. For the precision-weighted prediction error at the third level, we even get activation. And this is here the basal forebrain. These are cholinergic regions, and this here, the dopaminergic midbrain. So we see a kind of dissociation of the effects of different neuromodulator systems depending on the level of the hierarchy we have in the HGF. Now, some more recent data where we used EEG to look at a social inference task where a subject gets information from 2 sources. You have an advisor being a social source of information, and you have objective pie chart information, and subjects have to integrate this. Again, we have belief trajectories across the whole hierarchy up here, and then we see signatures of our quantities used in the update at different time points. This is a time axis, and this is basically a scalp location axis, and roughly this is posterior and this is anterior, and we see cue-related prediction error, negative advice prediction error, positive advice prediction error, outcome prediction error, advice precision, volatility prediction error, volatility precision. And you can see that in time, we're progressing through the HGF hierarchy. And this is a finding that I find absolutely fascinating. It also allows us to build basically a computational structure and overlay it on the brain, where we think these computations are taking place. And this is fMRI data localizing these different computations, localizing them in space, and here we have them localized in time. Another exciting new data set is by Becky Lawson in London. So she applied the HGF, a very similar task, not entirely identical, but similar to Sandra's task, to ASD subjects. And it turns out that their brains differ in their responses to HGF quantities in interesting ways. So this is the effective precision-weighted volatility prediction error. So this is again epsilon 3, which we saw in Sandra's study. On pupil diametry, she did pupillometry. So this is a very strong indication that this has to do with the noradrenergic system here, where healthy controls, so neurotypical subjects, don't show this huge spike in the weight on explaining pupil diameter through the volatility prediction error at the third level. So this is a very strong difference between, this very strongly dissociates ASD subjects from neurotypicals. Now, if you would like to practically use the HGF, there is a toolbox hosted at the TNU website at translationalneuromodeling.org TAPAS. There's a README, there's a manual, and there's an interactive demo. It's modular, extensible, MATLAB-based, and in the remaining about 15 minutes, we can have a quick look at this toolbox and do the interactive demo. So I will first have to get my mouse back. Oh, here, but how can I? Oh. Here we are at the MATLAB prompt. Let's make this whole screen. You download the toolbox, and then you can just go TAPAS HGF demo. And then just by pressing enter, it'll take you through the whole interactive demo. So first we will load the example binary inputs provided in the example file. You can see the commands that it does in the background here. So it just loads this example file. Now we'll find the so-called Bayes optimal perceptual parameters for this data set. Bayes optimal in the sense that this parameter set that we're going to find minimizes the surprise experienced by an agent getting this particular input. you can see the toolbox at work. This is the BFGS algorithm optimizing this here. And because it's very simple application in this, we will see more complicated ones, it's finished quite quickly. So you can now use the optimal parameters as prior means by adapting the config file. And you can see the manual. There's a PDF manual, and there's also lots of documentation in the code itself that shows you how to do that. So we can go and simulate now a non-optimal agent response. So we just pretend we have a subject. We choose a certain parameter level, and the numbers you have to look at are here, -2.5 and -6. So those are the two parameters, omega 2 and omega 3. And we're going to simulate with these. And now we visualize the simulated trajectory. So what you see here is the output level. You basically have the inputs in green, the subject's decisions in orange, its inferred belief in red, and the learning rate in fine black here. This is the second level. This is basically just a sigmoid transform, or basically this is a logit transform that gets you from the red to the blue, or a sigmoid transform that gets you from the blue to the red. And here we also have the uncertainty about the belief. And at the third level, you can see the volatility. Now, we simply go on. And the syntax of this simulation is also documented in the manual. So let's try to recover these parameters by fitting the corresponding models to the simulated data. I will just close, or I'll get that to the... So we're trying to recover -2.5 and 6. And you can see the estimate is at -2.45 and -6.02. Is that good or bad? How good is it? Does that inspire confidence? Yeah, I see you wagging your head. So the answer, of course, is we can't say just from doing it once. What you have to do is you have to do this 10,000 times or 1,000 times, and then you have to look at the distribution of your estimates around the ground truth. And we did this in a paper that came out in 2014, and we found that for realistic parameter settings, this basically works. We can recover parameter values with reasonable precision. So, now, just to do some diagnostics on the estimation, we can look at the posterior correlation, and we can see that among each other, these two omegas and the decision noise zeta, they don't correlate a lot, and that's good. So in general, also I would only recommend worrying about posterior correlations if they go very high, so very close to 1, or very low, very close to -1. But here we're certainly doing fine. Then you can also find all these measures in the fit object. So the estimation returns you an object est, and you have everything in there. You can look at it numerically, what we just looked at. Graphically, you have the covariance matrix sigma here, and you have all the parameters also stored here. You also have all the prior settings, so nothing is lost. You always have everything in your est object. So you can look at the parameters separately by name and as a single vector. And now you can also look at the trajectory of your inference. And if you remember the simulated trajectory, then it's clear that it's very similar to the one we were trying to recover. You can find all kinds of trajectories in the structure est-traj. So these are the means of the beliefs. These are the variances of the beliefs. These are the means of the predictions. These are the variances of the predictions. And these are various quantities that appear in the precision weights on the prediction errors. And we have the deltas, the prediction errors themselves here in dA. So let's try to fit the same data using a simple Rescorla-Wagner model. There are many, many models in the toolbox. Rescorla-Wagner is, of course, one of them. There's also Sutton, there's Peirce-Hall, there are many others. There are also hidden Markov models, hierarchical hidden Markov models. Many models, not just HGF models, are in the toolbox, so you can use them for comparison purposes. And if your favorite model isn't in there, the toolbox is modular, and you can very simply add them. So this is posterior correlation for Rescorla-Wagner. Just two parameters that we're fitting. One is alpha, that's the learning rate, and zeta, again, the decision noise. Not very highly correlated, so everything's fine. And this is the Rescorla-Wagner trajectory. Again, the inputs in green, same as before. Now, the decisions simulated on the basis of Rescorla-Wagner are in orange, and the inferred belief by Rescorla-Wagner, or the inferred value, we have to say, because it's a reinforcement learning model, in red. So let's move to continuous data. This was binary inputs, so this was just 0 and 1. The green dots were either at 0 or at 1. So let's load the exchange rate data we had in the talk, the US dollar and Swiss franc data, and let's find the Bayes optimal parameters here. This will take a bit longer. Now, you can see how the toolbox more or less easily fits 1, 2, 3, 4, 5, 6 parameters. You can even go higher. And the general thing is you can always fit basically arbitrarily many parameters as long as you have good priors. The more parameters you have and the less identifiable these parameters are, the tighter the priors will have to be that you put on. But basically, there's no limit to the number of parameters you can fit if you're prepared to come up with priors. On the other hand, if you don't want to estimate a parameter, you just want to fix it to a certain value, the toolbox lets you do that very easily, simply by setting the prior variance to 0. And then this parameter drops out of the estimation. The toolbox notices that automatically. Now here, the optimization algorithm has reset itself. When it gets stuck at a point where it finds it difficult to calculate the gradient, then it jumps back 1/10 of the way to the prior mean and starts again, and now it's converged. This usually gets you out of the hole. It always calculates the log model evidence. It does that by using the Laplace approximation. So when it finds the maximum a posteriori estimate for the parameters, it calculates the Hessian at that point. This is the only time it calculates the Hessian. And calculating the Hessian is costly, as you've just seen. It takes a bit of time. And using that Hessian, it can give you the log model evidence, or at least the variational free energy, which is an approximation to the negative log model evidence. It also gives you AIC and BIC, but since you've got the log model evidence, you will want to use that, because AIC and BIC are simply approximations to -2 times the log model evidence. Again, the posterior correlation, everything fine. All correlations are near zero. So this is what the Bayes optimal parameter setting gives us. An agent that uses the parameters that minimize its surprise at the input will have a belief trajectory that looks like this. So we now simulate other agents with slightly different belief trajectories, and we play the game of recovering their parameters again, now with a 3-level model. Before we just had 2. And then we go and recover parameters. So here the interesting quantities are -13 and -2. Let's see if we get there. Many more parameters being estimated here than before, so it takes a bit longer. We'll be finished right on time. Okay, while this is running, if there are any questions? Many. Rafal.
Very clear talk. So I have a question to the parameter pi u. So
Yes.
Do you actually estimate it, or do you assume it fixed, or do you kind of use the fact that the outcomes are binary to work it out what it should be?
I'd have to check whether I'm estimating it here, but you can estimate it. It's very simply configurable. Yes, you can estimate it. And in many applications we do, yes. Yeah. In some we don't, because we have a principled idea about what it will be. Yeah. So in some psychological experiments, you just know the precision with which stuff appears, and then you can fix that parameter.
Okay, thank you.
Yeah.
Well, mine is a bit more conceptual, probably. So it's not like related like to this specific example. Would you say that in principle, any sort of hierarchical model could be shrinked to a single layer kind of like model where you have, I don't know, some sort of dynamical system with couple differential equations, different time constants, whatever sort of flexibility you need, but where you can't really see different layers, different levels, or you can't really describe it as easily in terms of hierarchy?
I think you would run into severe problems. Maybe the easiest illustration is the application of hierarchy in multi-subject studies, where you have, I don't know, 100 measurements from each subject, and you can regularize the inference on each individual subject with measurements from other subjects. And that is the huge advantage of having a hierarchy, that the top-down predictions regularize, contextualize what the lower level does. And I don't think it's an accident that evolution came up with a brain that works in a hierarchical fashion. You perhaps could build something that does the same in the end, but it would be much more complicated and certainly much more brittle and much more prone to overfitting.
Just so I didn't quite understand, so how, because what you showed was how the optimal observer would do it, and how do you then go to fitting this to data?
So there was a step in between. I just took some arbitrary parameter values and simulated an agent using these values.
But so there are 3 parameters, because I thought it's optimal, so I didn't quite understand.
Yes, so sorry for going too quickly there. So what we first did, we just took the inputs that we had from our experiment or from our observed time series, and we asked ourselves, what parameter setting would lead to the least surprise on the part of an agent seeing this input? And then we found that parameter setting. Now, the agents that we actually observe will have different parameter settings because their optimality will be tuned to a much broader range of situations than just this task. Because if you're looking at the Bayes optimal parameter setting for one particular input sequence, this is overfitting the world with respect to this input sequence. But it is often useful to use this Bayes optimal parameter setting as a start for estimating the parameter settings that your subjects actually had. That's why it's useful. And then we just simulated some subjects that we didn't really have. We just invented them, and then we tried to get back the parameter settings we put in. The advantage there being that we know the ground truth because we put it in, and then we can judge whether we could recover that.
My question is related actually to this topic. So it seems that there's this claim of optimality, and I always wonder what exactly is optimal. And so in two senses. First, there are different priors, so depending on your priors, you make different inferences.
Yes.
So it's not clear to me what would be an optimal prior. But then on the other hand, this is approximating Bayesian inference. So we are not getting the absolute best possible inference. So in which sense it is meant to? So the question will be first, what is the objective function that
the objective
you
function
use,
is simply,
and why would it be optimal if you are using approximate inference?
Yes, yeah. So the objective function is simply the surprise, the Shannon surprise, the minus log probability of the inputs. That's what we're optimizing then. And as I said, it's only optimal in the sense that for this model, meaning this likelihood and this prior, you cannot find a parameter setting that will give you less surprise. So it's basically, the optimality is conditional on the model that you're using. It's not in any absolute sense optimal. And I don't think it would be hard to define some kind of global optimality, because optimality will at least always be task local. It will always be for this task optimal. So it's basically, it's conditioned on this task and this model. That's the parameter setting that gives you the least surprise with this model and this task.
Even if it's approximate.
Yes, because this is what this model does. In the colony, it's conditioned on this model. Yeah. Further questions? I just keep pressing enter. We now have somewhat of a correlation between omega 3 and pi hat u. We could examine this further. This is probably why it took a bit longer. We never know what happens because this is based on a random simulation we just ran. So this seems to be actually the trajectory looks absolutely fine, but you saw it took quite long. So there are sometimes problematic subjects and mostly less problematic subjects. Yes?
So we are a little bit behind schedule, but Christoph also started with about 10 minutes delay. So either we can go on if you have more questions anymore. Okay, so Christoph, are you finished? So are you happy now?
Yes, basically. I mean, there's nothing. It's just more of the same here.
Sorry, I'll ask you. Who won? Yeah.
Thank you. So if I understand correctly, there's an assumption that volatility is drifting just according to a random walk.
Mm-hmm.
But then I think you also showed that you could model volatility as having these discrete jumps. Is that correct?
Well, they look as if they were discrete.
Okay.
But actually, they're modeled as continuous. So when surprising stuff happens, you get these jump-like changes, even though the model's continuous. And I think that is one of the great features of this model, that it can deal with sort of discrete state transitions in the environment without having to have a fine-tuned model for exactly this kind of state transition. It's a generic model that can deal with all kinds of continuous change, but also sort of, you know, you're in a new world now, so you have to adjust all your learning rates upwards until you've adjusted to that new world.
I could imagine that in some contexts, maybe just a change of context or a new cue could signal to the organism that, you know, maybe it should expect other quantities to change. And does that map at all onto this approach?
So this approach is based on continuous change in principle. So, and what we can show is that it also works with basically categorical changes in the environment. Of course, I can imagine models in what's going on, especially if you are now back in a context that you remember. With these models here, you would have to relearn the new context. But if you're back in a context that you remember, so you can just sort of swap out your parameter settings for new settings that you already have stored somewhere. So such situations will be very interesting to model, but the tools that I showed today don't do that.
Okay, so as I said, we are behind schedule. There is time for one more quick question.
Thanks, Christoph. Great talk. There's a fair bit of documentation, like you mentioned, in the code and the great kind of manual you have. But one thing I guess I found with using the toolbox, especially the kind of the model structure that you get out, is that it's a bit difficult figuring out what some of those things are. Is there
a bit difficult
to figure out what some of these parameters actually are, what
they
represent? Is there plans to
expand the documentation
a little bit? Yeah.
Okay, I'll take that as a.
I'm not asking whether you can do it or anything.
They wish to improve the documentation. The point's well taken. I will try to.
Is there a plan to stick this on GitHub or something like that, so there could be kind of public or user contributions to it?
It is. Okay. User contributions.
Fair enough.
Can I come to your? Can I preempt what you're going to say?
Yes.
So Tapas will migrate to GitHub anyway. So not just the HGF2, but the entire package will go to GitHub in the near future, and then there will be a wide range of functionalities that may or may not include user contributions. That is still to be decided by the Tapas Council headed by Eduardo.
Okay, yeah, that's great news. I didn't know that. And I didn't want to get Klaas in a pickle by promising anything, but
I hope you're right with that. It's a discussion we've had recently, and
I'm totally all right with that. I'm totally all right. So user contributions are welcome. Yeah, absolutely.
All right. So let's thank Christoph for the great talk.